Hey YouTube, I'm going to be doing some calc-based physics problems. This is just the beginning of the course though, so I'm going to show you a different approach of how to solve some of these simple physics problems. Something that my professor showed me, which I think is a lot better. And if you have a time test, it actually takes a lot less time instead of trying to plug in all those kinematic equations. So that's my opinion. So what we're going to start off is with this problem. It says you're driving at 29.1 meters per second when a truck ahead comes to a halt 200 meters away. Your brakes are bad, so you deaccelerate at 2.4 meters per second squared. And the first problem is how close do you come? The second one is how long does it take for you to come to a stop? So usually you turn to your kinematic problems, but in this one I'm going to draw a velocity versus time graph. So we know that we're traveling at 29.1 meters per second. And we know we constantly deaccelerate. So I'm just going to draw a straight line down. So we know from calculus, and we know from just what we learned so far, is that this area under the velocity versus time graph is our delta x. So that will help us out in the beginning first. So it wants to know how close do we come and how long does it take. So the only thing we know on this graph is the velocity and nothing else really, so that ain't going to help us. So then we could draw an acceleration versus time graph. Well, we know it's deaccelerating at 2.4 meters per second constantly. It's going to end at some time. 2.4 meters per second squared. And we know that the area under this graph from calculus and what we learned in the course so far is our delta V, which equals 29.1 meters per second. Well, now we don't really have a physics problem anymore, we just have a geometry problem. So we know that the area of a rectangle is base times height. We know the area is 29.1 meters per second equals the base, which is our time, times the height, which is 2.4 meters per second squared. Then our time equals 29.1 meters per second all over 2.4 meters per second squared, which equals, I got 12.1 seconds. So then we come back here and plug that 12.1 seconds in. It just becomes another geometry problem. So we already solved step number 2, which is 12.1 seconds. So now all we have to do is find how far it was from this. So we know that the area equals 1/2 base times height, the area of a triangle. So we know that the area equals 1/2 times 29.1 times 12.1 seconds meters per second. Well, this just comes out to be, I believe it comes out to be 176 meters. So now if we want to find the distance the car stops, how far it is behind the truck when it comes to a complete stop, we'll just use the initial, how far it was, minus the final, how far it traveled. And that will give us 24 meters. So that's the first problem. So the first step we want to do is draw velocity versus time graph and see what we can work out from there, because from the velocity versus time graph we can get to the displacement versus time graph, or even the acceleration versus time graph, which we did in this instance. And we got the time, and then if we got the time, it was just pretty straightforward because we already knew the velocity and the time. So then we could find out the displacement of the car after 12.1 seconds, which was 176 meters. And then we could figure out how far it was when it came to a complete stop from the truck. So now in the second example, which I'm going to set right here, it's a little more interesting. It involves NASCAR. Maybe for some American fans like this. So it says, The fastest speed in NASCAR history was 212.809 miles per hour. If the race car deaccelerated from that speed at a rate of 8 meters per second squared, how far would it travel before coming to a stop? So the first thing we gotta do is convert this to 212.809 miles per hour. That equals 95. Let me see what I got right here. 95.13 meters per second. So then again, first thing we want to do is draw a velocity versus time graph. We can see that it constantly deaccelerates at 8.8 meters per second, but its initial velocity is 95.13 meters per second. And we don't know the time, but some time t. So we don't know delta x either, which we know is the area under this graph. But we do know the acceleration and the velocity. So let's draw an acceleration versus time graph. So you know it's 8 meters per second squared constantly at some time. We'll just stop it right here. The only reason I stop right here is because there's really no reason to keep going, because we know it's going to come to a complete stop at some time, and that's what we're trying to find out. So then we know the area under this equals delta V, which equals 95.13 meters per second. So then it's just geometry problem. So we know the area of a rectangle equals equals base times height, which is 8 meters per second times our base, which is our time. So then we know our area is 95.13 meters per second all over 8 meters per second squared, and that came out to be 11.84 seconds. So we're going to put 11.84 seconds right here. And then we can find our delta x right here, how far it did travel. So then we're going to do area of a triangle equals 1/2 the base times the height. Well, that just equals 1/2 times 95.13 meters per second times 11.84 seconds. Well, that just comes out to be, I believe, 207 feet per second. 207 feet. Meters, I should say. And now we figured out just how far it did travel from 295 meters per second to a complete stop, 0 meters per second. And we proved that using our velocity versus time graph. So that's the very first thing you do is you draw your velocity versus time. And then we couldn't really do anything with this, so we needed another graph. So we drew an acceleration versus time. So we knew our acceleration was 8 meters per second. We didn't know our time, but we knew the area of this rectangle, which is our delta V, equals 95.13 meters per second. So then we could find the time. After we found the time using our acceleration versus time graph, we plugged that time back in over here and found our displacement using the area of a rectangle, because we know the area of this rectangle, or of this triangle, sorry. We found the area using the area of this triangle, so we know the area of this triangle equals our delta x, which is 207 meters.